When you first encountered Taylor series, you dealt with a very specific type. You dealt with something called the Maclaurin series, and that's from Core Pure 2, Chapter 2. The idea behind that was we can come up with a polynomial, albeit an infinite polynomial potentially, that describes and represents the function that you're interested in, and it gives a good approximation to the function, specifically when you're close to zero, close to the origin. So if you've got something like a sine wave, you could represent that sine wave with a function like x minus x cubed over 3 factorial, and that function will closely mimic the behavior of the sine wave, at least provided x is close to zero. However, if we want to go beyond that, or we want to approximate the value of sine x for some other value of x, we'll find that our estimates from the first few terms of the series expansion get increasingly inaccurate to the point where they're basically useless. The purpose of Taylor series in general, and these two alternative versions that you come across in Further Pure 1, are to allow us to deal with a function at other places than zero. So we think of these as being centered at somewhere else. F of x centered at 0 will give us what's known as the Maclaurin series expansion, the one you see at the top. And the way we calculate that is to start by differentiating your function a bunch of times. And if it's something like sine or cos or e to the x, then you can often find an efficient way of generating ever higher derivatives because there'll be a pattern involved. And then we just apply this formula. The formula itself comes from what happens if you assume there is a polynomial that works, and then you differentiate repeatedly, sub in 0, and see what happens. Everything will cancel down to give you the value of the different terms, the constant, the coefficient of x, the coefficient of x squared, and so on. Now, there are two different forms that you'll come across for Taylor series in Further Pure 1, and that makes it rather confusing, particularly when you're first learning it. So I'm going to try to demonstrate what's happening with these two forms using GeoGebra. The first version you see just below the standard Maclaurin series one is f of x plus a. And this one is essentially still Maclaurin series expansion, but it's Maclaurin series expansion for a different function. It's the function g of x, which is defined to be equal to f of x plus a. That essentially means g of x is a translated version of f of x. We've moved f of x to the left by a. And that means we've got a different function. And if we look at what happens at the origin for this new function, it'll be different to what happens at the origin for f of x. So over here, we have the sine function. And I'm going to drag it to the left a little bit so that we can generate an alternative function, g of x. So this is g of x. G of x is the same as f of x plus 2. It's the same function as the original one, apart from the fact that it's been translated to the left by 2 places. And that means we've got a whole different thing here, but we still have the capacity to do Maclaurin series expansion at 0. 0 was the thing that let us calculate those values, so it makes sense to try to do the expansion centered at 0. Things cancel out nicely. So we calculate that at 0, and we get this. And you'll notice that looks different to the sort of expansion we would have had if we'd left it at the origin. In fact, you can see if we drag it back to the origin, this is going to give us that more predictable x cubed type curve that we would have expected. If you expand at the origin, you basically get the Maclaurin series expansion. But if you expand somewhere different, we drag it to the left a little bit, then we're going to get some slightly different expansion. And each of these is going to be the expansion of my new translated function, but still centered at 0, which means they're going to work best when the number you put in is close to 0. Now, the next bit is where things get a little bit clever, because yes, we've found a way of representing this function perhaps differently to what we had before, because we've shifted it to the left and then put in 0. But really what we care about usually is the original function back at the sine x. And to do that, we shift back the other way. What's clever about this is we've pulled the function to the left in order to apply the Maclaurin series expansion idea at the origin, and then we shove the Maclaurin series expansion back over to the right so that it matches the original function once more. What we're looking at now is still an approximation for sine x, but it's an approximation for sine x which is closest when x is equal to 2. So unlike, let's say, your small angle approximations that give you a good approximation for sine x whenever x is close to 0, this is a good approximation for sine x whenever x is close to 2. And you can see the difference with the expansions. When we do g of x, f of x plus 2, we still get an expansion with ascending powers of x. There's an x there, there's an x squared here. Whereas if we then translate back the other way, it means everywhere we see an x, we're going to replace it with x minus 2. That's how we can turn f of x plus 2 back into f of x. So translation back the other way. But that also means that everywhere we had an x in the expansion, it's going to turn into x minus 2. So x squared becomes x minus 2 squared. Back here, we can see the effect. F of a is the overall result of shifting and then applying the Maclaurin series expansion. So the only real difference between the first line here and the second line is that we have f of x plus a instead of f of x, and then f of a, f dashed of a, etc., etc., wherever we would normally see f of 0, f dashed of 0. To go from the second to the third version, we replace x with x minus a. So the process is shift the graph, apply the Maclaurin series expansion techniques to get an expansion at the shifted graph, and then shift your expansion back the other way, and you'll get an expansion for your original function, but it will be centered at wherever the new value is. So I've tried to describe this here using this Greek letter called epsilon, which is often used to represent a small quantity. So originally we had f of x for x close to 0, and that gives a good approximation for the value of f of 0 or f of 0.1 or f of minus 0.2, something like that. It's going to work well if you're trying to evaluate f of a number close to 0. The next version is the translated version, and that will allow you to get a good approximation for f of something close to a. And this could be enough, because you'd still sub in x equals 0 to get that, because f of x plus a will be close to f of a only when x is close to 0. And that's because this one relies on the Maclaurin series expansion for a translated function. If, however, you want to go back to the original function, so you have an expansion that is specifically for the original function f of x, then you apply this translation, you do a substitution, so you replace x with x minus a, and we get back to this. And again, it does a similar thing, because this one in the middle gives us values close to a, and this one at the end also gives us values close to a. If we put in values for x if we put in 0 here, it'll give the same effect as if we put in a here for x. We're finding values for f of a, or f of something slightly bigger than a, or f of something slightly smaller than a. So both of these new ones, the value of them, the power of them, comes in the fact that we can calculate a good approximation for the function at any input we like, or close to any input we like. So back here one more time, the original function looks like an ordinary sine wave. We can shift it, pull it to the left by a certain amount, find the appropriate polynomial that matches the origin here. So this will always be as good as it can be at 0, and increasingly bad the further away you get. And of course, shifting to the left doesn't have to mean to the left. You can pull it to the right if you prefer, but we can think of this as a horizontal translation, however we do it. And then we reverse that horizontal translation, and we do exactly the same thing. So this is just a translated version of the expansion that we previously calculated. That way you can have two different alternative ways of doing this. You can either find the expansion for f of x plus something or f of x minus something if a happened to be a negative. And then from that, you could evaluate, find an approximate value for the function at a particular point. Alternatively, you could do the final step where you substitute x minus a into the formula, and you'll generate your expansion in terms of powers of x minus a.